Hi, students. If you are starting this lesson, then that should mean that you have already plotted all of the stars on the HR diagram, the Hertzsprung-Russell diagram on the last lesson. And I want to just start off with this lesson by doing a little bit of a review. And these points are things that I am expecting you to know at this point in time. So if there are things that I mention on this slide that you're like, what is he talking about? You should probably come chat with me if you're in school on a certain day. And if you're cohort C, you should email me because I want to make sure that I get everybody in my 2 freshman classes up to speed on these things. Okay, for our first point, this one's a pretty easy one. What this is basically reminding you of is that astronomers categorize all of the stars that are up in our galaxy and in the universe at large. And they do that based on the star's surface temperature, which translates to different colors. Because remember, the hotter stars emit different colors than the cooler stars, even though the coolest stars are still really hot. I want to make sure, I think you all know that, but even the coldest stars, and that's a really silly way to describe a star because no star is cold, but so I guess I'll say the coolest. Even the coolest stars are, so hot that if you were to be on the surface of them, you would be dead in a second, right? Okay, so we have that clever little phrase that we use to remember the order of those spectral classes. And I told you guys in class already, I do not use the old-fashioned phrase that astronomers used to use because I think it sounds a little bit sexist and a little bit insensitive. So I go with something that will only offend giraffes, and that is, "Oh, be a feisty giraffe, kick me." Remember that phrase, use it a couple of times, so that way you nail such a question on a test, because you should know these spectral classes in order. Class O stars are the hottest, and class M stars are the coolest. All right. Once, besides those 7 classes, we go a step further because, for instance, there are a bunch of stars that are grouped into stellar class G, for example, but even in that group, there is a wide range of temperatures. So we further divide them into 10 more categories each, and we do that with numbers. So 0 would be the hottest stars of a certain group, and 9 would be the coolest stars of a certain group. For example, going on to bullet number 3, our sun is a G star, but it's relatively hot. If you were to compare it to other G stars, it's one of the hotter ones, and so we designate our sun as a G2 star. Okay, if our sun were a little bit hotter, it would have jumped up into category F, and we would have had a class F star, and that might not have been such a good thing for the Earth, because that means that the sun would have been putting out more radiation, and Earth would have evolved differently, and we might not be here today learning this material. Okay, bullet number 4. All stars, even the coolest ones, are easily hot enough to emit white light. That is to say, they emit all of the colors of the visible spectrum. I hope by now, as 9th graders, you know what the visible spectrum is. If you don't, I promise you have seen it. If you've ever seen a rainbow, then you have seen all of the colors of white light. A rainbow is an atmospheric phenomenon where it takes white light from the sun and refracts it in such a way that it casts the various wavelengths of white light across the sky. So you see your violet and blues and greens and yellows and oranges, right? Okay, stars, even the coolest stars, so even the red stars, are still plenty hot enough that they are emitting all of those colors. And when anything is hot enough and it's emitting all colors of the visible spectrum, it'll appear whitish. Now, I say that because if you go outside at night and you look up at the sky, yes, you will see different tints. Some stars look a little reddish, some stars look a little bluish, some stars look a little yellowish. But I think everybody can agree that overwhelmingly, all the stars generally look whitish. Okay? All right. If you don't believe me, go out tonight and look. Okay, I had a little typo here. I want to fix that. Don't like typos. All right. Bullet number 5. The tint or color of a star can give the layman. Now, a layman means people like you and me. We're not professional astronomers. Yeah, I know a thing or two about this because I've been teaching it, and I love this topic. But you guys are laymen. You're coming into it kind of new. So, the tint of a star can give you clues about their temperatures. So you should go out tonight if it's a clear night, and you should look up, and you should look for the stars that look a little reddish and compare them to the stars that look a little bluish. And that's letting you know right away, oh, those are stars that have different surface temperatures. It's kind of fun. Okay, going on to the next bullet. Astronomers have they can take it a step further. They don't just go outside and say, "Oh, there's a red star. That one's kind of cool." They have these special tools that literally collect the light from the star, and then they can pinpoint. They can nail down the surface temperature of that star right down to the Kelvin, right? So for instance, they know that our star is 5,000. I'm rounding off a little bit here. Our sun is just a little bit cooler than 5,800 Kelvin. Pretty hot. Okay, but make no mistake about it. There are some stars that are upwards of around 20,000 and even 30,000 Kelvin. So they are ridiculously hot. All right. You also should know by now that astronomers love using parallax. When they can measure a parallactic shift in a star when viewed from different parts of Earth's orbit, they can pinpoint that star's distance from Earth. And they love when they can do that, because if you know how far away a star is from our solar system, then you could figure out how bright that star truly is. And that's important. Okay, because if you know how bright a star truly is, okay, if you know this, you could then go on and express its brightness in luminosity, which, as you already know, or I hope you already know, we love to express a star's luminosity in solar units. We do that a lot. Okay, it's just very convenient, and it makes astronomy a little more accessible to everybody. Okay, so I hesitated on whether or not I should show you this slide, but I'm going to go ahead and I'm going to do it, because what this is kind of, I say kind of, this is kind of a key for the work you've just done with that last assignment. However, and listen very carefully, you cannot take this and place it side by side your graph and think that it's going to give you all the right answers, because I made this key a couple of years ago when the stars that I gave you on a data table were a little bit different. So there's going to be some dots here that you might not have, and you might have some dots that are not on here. And I do not want you to be stressing yourself out and being like, "Oh my God, I did it wrong." Stay calm. It's all good. However, overwhelmingly, you should have a pattern that looks a little bit like this, where you should have stars that start up in the upper left and stretch all the way down to the lower right. And then you should see a small grouping of stars up here in the upper right. And you should see a small grouping of stars down here that are close to the center, but down lower. Okay, if you don't have that pattern, then something went wrong. All right. So this exercise that you did, I designed it so that you would be literally walking in the shoes of two scientists over 100 years ago. I hope I can pronounce his name right. Ejnar Hertzsprung and Henry Russell. So Hertzsprung was from Denmark, and Russell was an American astronomer. And the two of them were doing very similar research. They weren't working together. They just both were doing very similar research. And we can kind of say that the research they were doing probably started off at first as almost a confirmation study. They were expecting certain things to emerge when they set up that graph, that Hertzsprung-Russell diagram. And let's see how that all unfolded. Okay, so they had I'm simplifying this graph. It looks a lot more elegant than the one you guys dealt with the other day with all those lines on it, right? Remember though, temperature increases as you move left on this graph, which is kind of unorthodox, while luminosity follows the tradition that it increases as you go up. So I'm going to say that one more time. On this graph, luminosity gets brighter and brighter and brighter as you move up, and that's pretty typical with graphs. However, temperature is reversed. Usually we're used to values growing as we move towards the right, but on this graph, as you move towards the right, temperatures are getting cooler, okay? You're just going to have to accept that and move on with that. All right, so what did they expect to see? Well, they certainly didn't expect this, right? I'm not showing you right now how the plotting was expected to look. I just threw these stars there because if you were doing this in class on the smartboard, you would be walking up and you would be moving these little stars with your fingers and showing me if you understood whether or not to show me whether or not you understood what they expected to see over 100 years ago. So I'm just going to go ahead and show you this is what they expected to see. They expected the blue stars to be really exceptionally hot and bright, so they should be in the upper left, whereas the red stars should be exceptionally cool and dim. Okay, so that's what they expected to see. Okay, and by and large, they did see that. Roughly 90% of all of the stars that they graphed fit this pattern. But as so often occurs, the universe had some surprises for us. And they found this. There were some stars that were ridiculously bright, even though they had relatively cooler temperatures. These stars up here. And they also found some stars that were ridiculously dim, or I should say, surprisingly dim, despite their hotter surface temperatures. And those are down here. Not many, roughly 10 to 11% of the stars didn't fall into that main path that we see. Okay. About a little over 10% fell into one of these two categories instead. Okay, that was a mind-blowing discovery. And so I ask you, and I really hope that when I ask you guys to pause and think and try to answer questions, I really hope you're doing that. I hope you're not just letting me go on to the next slide and answering it for you. Remember, it's just like going into a gym. When you go into a gym, you've got to do the weights to get stronger, to get fitter. You can't let somebody else do the working out for you. So you should pause right now, and you should try to ponder and think about a possible answer. How could it be that a cool star could be bright? And how could it be that a hot star could be dim? And I want to give you one hint. Remember, distance is not a factor here, because what astronomers are plotting here are only the stars for which we know their true distances. And therefore, we know their true luminosities. So distance is not a factor here, okay? You can almost imagine and this is what astronomers do. They imagine all of these stars are at the same distance, and yet they are plotted this way. So what other reason could allow a cool star to be bright? And what other reason besides distance could allow a hot star to be dim? 10, 9, 6. Okay, here comes the answer. Bam. Astronomers realized, holy moly, there are some stars up there in our heavens that are ginormous. I love using that word, okay? And there are some stars that are really, really small. And that is why they are dim, because they're really hot, but they're so small, they're not putting out a lot of light. I like to use the metaphor here. Picture this big giant orange star as like a bonfire. Pretty hot, but as far as hot things go, not as hot as other stuff. But they're so big, bonfires are so big, you can see them far out, like from a ship. Like that's how they used to hail ships in. They would burn big bonfires on the beaches, and you could see a bonfire from far away because they're so big that they're putting out so much light. Whereas these little guys down here, think of these as like blowtorches, right? ridiculously hot flames. You would never want to put your finger in it. You would burn your skin off, right? But they're so small that the overall amount of light they put out is not that much. Can you imagine somebody standing on a beach with a blowtorch trying to hail a ship in to shore? Wouldn't that be kind of funny? You would never want to use a blowtorch because it doesn't make enough light for a faraway object to see it. All right, I hope that metaphor helps a little bit. Okay, now I want you to go back to those graphs that you made, and I want you to update them and label them accordingly. You're going to label those upper stars in the upper right as your giants and your supergiants, okay? And then you're going to go ahead and you're going to label those tiny stars down in the lower, in the bottom center of the graph as your white dwarfs. Even though not all white dwarfs are white, they are whitish. Some of them have a blue tint to them, but we categorize them all together as white dwarfs. And then any star that is on this big giant path here, we call it the main sequence. These are stars that are in the main part of their lives. Stars spend the bulk of their life on the main sequence. Our sun might be this one right here. Okay, we're going to imagine there's our sun. Okay, it is a main sequence star. And our sun has been there for about 5 billion years, and it will remain there for about another 3 billion years before it finally has properties that change that will mean it will start to be plotted in a different place on the graph. I'm going to give you a little more detail on the next slide, and here's how it is, because I'm going to be using these words in class, and you're going to be hearing these words on YouTube, okay? So scientists take it a step further. They call some stars on the main sequence blue giants, and you see those up there. I love those stars. They're just really wicked cool to look at in telescopes. Some famous examples of blue giants are Rigel and Mintaka. Okay, they're big, they're bright, they're blue, and they could be seen from far, 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 far away. Because even though they're not as big as supergiants, they're really ridiculously hot, and they're still pretty sizable, so they shine like bright jewels in the sky. Okay, you remember Rihanna's song, Shine Bright Like a Diamond? That's those stars there. And then in the upper right, you have stars like Betelgeuse, right? That's this big orange guy up here, or Antares. These are behemoth stars. They're bloated. They're on the last thresholds of their lives, and they're someday going to go boom. They're someday going to go supernova, but they are big, and even though they're cool, they're so big that they're so bright. Okay, and then we have these dwarf stars down here. Okay, now these they might be boring, but let me tell you, they dominate the universe. The vast majority of stars in our universe are red dwarfs and orange dwarfs. And then there's a fair amount of yellow dwarfs, like our sun. Our sun is a yellow dwarf, okay? But here's the crazy thing. If you go out tonight and you look up at the sky, you can't even see one red dwarf from your front lawn. Because even though they dominate the heavens, they're just not big enough and bright enough to be seen. In fact, the closest star to our sun is a red dwarf, Proxima Centauri. It's only 4.3 light years away, and we can't even see it with the naked eye. How crazy is that? Okay, I hope you enjoyed this lesson. I'm going to be throwing some questions at you to get you set up for success, and then we're going to move forward. Thank you.